Welcome to the MIT AI and Quant Conference's online learning series. Today we have a living legend with us, Quant Professor Carol Alexander, author of 5 books, editor of 20. When Rebellion Research conducted polls on the best quant professor, and data minds around the world, Carol received so many votes, she was quite frankly a data outlier. I have been a fan and looked up to Carol for over a decade. Everything she has written, I have been impressed with. And I think she's one of the most brilliant minds on the planet. And I'm totally honored to learn from her today. Thank you so much, Professor Alexander.
Thank you, Alex. That's a very generous introduction indeed. And it's a pleasure for me to talk about this subject to the MIT conference because it's so new. And for that reason, there's not a lot of traffic going to the paper that I've written. Let me share my screen so I can explain what I'm going to be doing. So this is my talk. And you should be able to see a thumbnail with me and the slides. So the paper is co-authored with Casey Chen, who used to be a PhD student of mine. She's now a faculty member at the University of Sussex. And I've also benefited enormously from a colleague that I've known since I was in the maths department at Sussex many, many years ago. Now I'm in the business school, as you can see. Peter Williams, who's an expert in machine learning. He left academia to develop proprietary machine learning tools for finding gold, and now he's very interested in the work I'm doing on rarity, which is what I'm going to be focusing on here. And also, you can see, if you just click any of these, I'll give Alex the links afterwards, but that's the paper which was posted not so long ago. It's an awfully long abstract, tells you everything about it. Perhaps that's why there's not so many downloads. But as I said, it's a completely new subject area. So, and one that's obviously zero quants. And I also, if you use this QR code, you can go to this group of people that I've got together. We call ourselves OutRank, where our contribution to something called OpenRarity is listed here. And a lot of the work I'm going to be talking about in this presentation has interactive, you can change to pudgy penguin, so you can turn on trait normalizations, and then you can look at other metrics. But anyway, it's difficult to understand this unless you look at the paper, and most importantly, I think it's these slides. So I'm going to give you a bit of background about NFTs in general, and then focusing on the digital art collectibles, which we also call personal profile pictures, or PFP. And then a survey of the way that rarity is measured. There's supposed to be that the price is proportional to inversely proportional to rarity. So the more rare, the higher the price. And rarity is sort of ranked 1 is the most rare, to say 10,000 if there's 10,000 mutant apes. So the lower the rarity rank, the higher the price should be. And some of these have gone for incredibly high prices, over $20 million. And they're sold in Sotheby's and things like that. And then we get technical. I'm going to be introducing the mathematics behind the rest of the paper, which explains why almost all of, there are many of 20 or so rarity ranking sites that many purport to do novel things or different things, but almost all of these are incorrect, and almost all are very similar to 1 or 2 methods. So that's the story of this paper. I'm sure this state of affairs will change once some mathematicians start working on the problems, but it seems that there's 0 mathematicians out there. So anyway, let's just introduce what non-fungible tokens are. So it's not like Bitcoin, of course, which, well, actually some Bitcoins are tainted because, they've got a history of being part of a hack or something, but nevertheless, we would say that, well, Ether is the currency of NFTs, because these are basically certificates of ownership encoded into a smart contract. And most of them are on the Ethereum chain, which means that the smart contract code is paid for in Ether, or small units that we call GWEI. It's the gas that fires these smart contracts that ride along these sort of motorways. So Ether is the native currency really for NFTs. And there are lots of different types. There's music, videos. Some musicians actually find that by making NFTs of their work, they're able to bypass intermediaries and therefore actually make a living out of being a musician. And they get royalties on resales and things like that. Tickets are NFTs, not just tickets to events, but also other forms of identification, like your passport will very soon be an NFT. And if, I don't really want to go along that route for too long, because within a few years, if Vitalik Buterin, who's this, he's a good guy. He's not like these centralized exchange cowboys. He's the founder of Ethereum, but people are getting quite concerned about where NFTs are going in terms of your whole life becomes something called a soul-bound token. So it's not just your birth certificate or your marriage certificate or your national service, but also the grades you got in school and any parking fines, or you know what I mean? That is very, very frightening. Anyway, I'm not going to be talking about that. Nor am I going to be talking about real estate, which has been NFT'd for quite a long time. So you may not be able to own an entire building in the City of London, but you could own a small share, and that certificate of ownership of a real physical building would be the smart contract that you buy. And then, of course, there's all the digital real estate, the metaverses, Sandbox, Decentraland. There's even one called Lieberland, which is really, really interesting. That's not a game. It's actually developing a metaverse for meetings. Right now, we Zoom a lot. We know it didn't used to a couple of years ago, but we do now. And it won't be long before we'll be meeting as 3D avatars in metaverses. And our avatars may cost a lot of money. And, that gives some indication of the person you are, that possibly the power. Or they may not have may not have cost a lot. In fact, they may have been airdropped free, like CryptoPunks. One of them went for 23 million, but originally they were airdropped free to the cognoscenti, the ones in it's all about community, So anyway, you can also buy land. I've bought Brighton Pier in Tillier because I think there'll be a lot of football there. I've also bought the London School of Economics and the Business School at Sussex, £20. But anyway, these are a lot of the market at the moment is people thinking, well, you never know, I'll spend £20. It might be very valuable if the university wants to buy it back from me in 10 years' time. And then there are these game accessories, sneakers, Nike and other sports companies are going for all sorts of patents now for their completely digital designs and for the avatars to wear. And then there's photography and art, physical and digital. You can own a bit of a Dali painting, even if you can't own the whole thing. But what I'm going to be focusing on is digital art. And in particular, as I said before, these collections, special collections, not the breedable ones. I mean, this is an even more challenging mathematical problem. But the simple mathematical problems, there's such a mess that we've got to sort that out now. It's easy enough. This talk does it. And how much is this ecosystem worth? Well, the value of the NFT sales in total last year was about $22 billion. Because they're denominated in Ether, it's difficult to measure because that was when we were translating S at the time, but the value of S went from 3,000 up to what did it go up to? About 7,000, I think, at one point. Yeah, that was its maximum. So now let's have a look at the market cap at the moment. So coin market cap, that's the standard sort of one of the ranking sites, covers everything, exchanges, cryptocurrencies, and so forth. It also covers NFTs. And you can see here that the top selling one at the moment is Mutant Ape Yacht Club. The volume is, in the last day, is around 327 S, so that's about 500,000. It's not huge, but there are thousands and thousands and thousands of these. So anyway, CryptoPunks is there, Bored Apes there. I'll talk about those two because they're the fairly well-known ones. So there are marketplaces. I'll have a look at the main one, OpenSea, but also exchanges, Coinbase, Binance, they're all trading NFTs. And then there are a lot of price and rarity analytics providers. And this is where I come in, because I'm an analyst. And I was asked to design a pricing model using proper type, machine learning algorithms and everything, bells and whistles. And so I looked at, because it should be related to rarity, the way rarity was measured, and then I stalled. I said, there's no way that we should put a machine learning algorithm onto these data until we sorted out the rarity. So this is my mission at the moment, because there won't be a clear, prices are going to be fuzzy all over the place, difficult to predict without the material I'm talking about here. Then there are generator algorithms. Some collections have better properties than others, as we shall see. Data aggregators, optimal order routing, lending platforms. You can use your Bored Ape as collateral. How on earth they value that collateral, I don't know, but you can. So, betting shops, see contracts for differences and everything. So it's a huge ecosystem. And although, of course, venture capital has more or less dried up the last few months, what with one thing after another, in the entire crypto ecosystem, we're in what they call a crypto winter, I would say, for at least the next year. I'm just making some predictions and writing some blogs myself about what I think is going to happen. Sneak preview. The Aave Lido axis is my headline for the great crypto crash of 2023. Anyway, that's DeFi. So back to NFTs. You can see OpenSea valuation of 13.3 billion in January this year in their Series C. They raised about a tenth that amount, about 1.5 billion. Then there is NFT Go, which is, I'm going to focus on that because it's just a ranking and marketplace. Then there's all sorts of others. There's NFT Bank for lending with collateral based on NFTs, data aggregators like Upshot. Nansen does all sorts of things. It's probably one of the best platforms in this area. And Magic Eden is another marketplace like OpenSea. So OpenSea is the main one at the moment, at least. There's a bit of a war going on with these marketplaces, to be honest. And they cover all sorts of NFTs, but most of them are in the collectibles. That's where most of the volume is. So if we look at the collectibles, that's an example of very rare CryptoPunk. It's got hardly any attributes. In other words, it's only got a hat. It's a rare skin type. It's a blue, that's alien. So this might be a very valuable one. And here's a Bored Ape with X-ray eyes. That's also quite a rare attribute. This is a CryptoKitty. I'm not talking about those because, as I said, they breed. And if we just look at the collectibles that they have here, I don't know, there's probably some recently launched ones. I didn't look at this before my talk, so Hippo Club, that's a collectibles. Bored Ape Yacht Club, Crypto, Punks, Cool Cats. I don't know. Shall we look at Cool Cats or Moonbirds? So here we are. You can see this marketplace, these avatars can go from anything, this one, the asking price, the buy now price is nearly 2,000 S, so that's nearly 2 million for that one. Can you imagine paying 2 million for that? Anyway, so let's go back to just focus on CryptoPunks. There's been a couple of versions actually. When originally issued by Larva Labs in 2017, these say 0 attributes. They actually have 3 because the gender, look, that's female, that's male. They have the background color, purple, and then they have skin color, which isn't just, I mean, there could be about 5 different backgrounds. I think there are 3 genders because it includes aliens. Oh no, aliens are just the skin type. So about 5 different skin colors. So they all have at least 3 attributes, and then they've got additional ones. These are the minimal ones, and here's a maximal one. It's got 7 additional attributes. It's the only one with 10 in total, and it's never been sold. But you can see that the pricing, this is the symbol for S, these 3 little lines here. So the average sale price hovers around 2,000 S. Floor price is lower. The floor price is because they're sold by auction. So it's automatically set as the last traded price, but of course that can differ quite a lot according to the rarity of the attributes that these images have. And when you set the auction, you can set a buy now price if you want, and you can also set your own floor price and the length of the auction. So one of these, not this one because it's never been sold, but one of these very rare ones sold for 23 million. It wasn't even one of those. I think it was one of those with 4 attributes. So that's Larva Labs. We can see that it's actually, they've original CryptoPunks, so they had quite a few others, MeBits. And so you can trade, this is probably the main marketplace rather than OpenSea for CryptoPunks, but actually Larva Labs is selling out to Yuga Labs. They started Bored Apes. Here you can see some examples of just solid gold fur is very rare. Dagger mouth, also very rare. This type of hat. And they weren't dropped free. But they were all 0.08S. So when you first launch a collection, you don't know what you're buying. So I could have showed you one OpenSea, but you can see for yourself. You just go to a new collection and they all got the same picture, and you don't know what the rarity is going to be. So it's a bit of a lottery. It's a bit like buying a Pokemon pack and sorting through for the really rare ones, you know. But anyway, they were only 0.08S back in 2021, at the beginning, actually. That would have been 20 quid or something. And some of these, I think the highest price paid was 3.4 million. So the traits are background, can have lots of different attributes there. It can be grey or orange or yellow, as you can see, and many other colours. The clothes, pyjamas, army outfits, things like that. Earrings, including none. Like this one doesn't have an earring, so none is an attribute for earring. Also for hats, they don't all have hats. Eyes, they all have eyes though, and they all have fur, they all have mouth. So there are 7 traits, and as I said, some very rare attributes. Now this is quite an interesting collection because it was the generator used, made the trait distributions independent. And that's quite important when it comes to measuring rarity, as we shall see. So now we're looking at the rarity, the way that rarity is measured. And I'm going to take you to Rarity Tools, which is probably the most advanced. Let's have a look at, I don't know, CryptoPunks. There's CryptoPunks ranked by rarity. You can see a lot of aliens there. And we can look at Bored Apes or Mutant Apes. And then you can see they've got this experimental well, some of them have an experimental one. Some of them, I don't quite know. There's not very much documentation. But anyway, it's possible to understand how these methods rank. So this is number one by using something called Rarity Score. And you can see this one's psychedelic is number 5, and there's that one I showed you, it's number 9, and so forth. There's a dagger mouth, number 10. Or we could use average rarity. And this one's still number 1, but where's that? I mean, the others are completely different. Or we could turn on trait normalization, and it completely, oh, there we are, that one's back again. So, or we could use statistical rarity. So the point is that, you know, the method you use, and there's no documentation about trait normalization. So we don't exactly know how it's done, but you could have one, and there is one actually we looked at that is incredibly rare according to the arithmetic one that Nansen used, and really, really common according to the thing that's called trait rarity. So basically, there's no point in using any of these rarity metrics at all because nobody understands them. So, and then come OpenRarity. And this is a collective of Coinbase and all these other collections like Pudgy Penguins, Cool Cats, OpenSea, IC Tools, that's another ranking website, X2Y2, so marketplaces and rare, and this is a very nice looking design. Rarity does not have to be confusing and opaque. So it says, rarity calculations have historically been produced in closed source environments and can diverge across publishers. Yeah, even on the same one, Rarity Tools gives you that. Anyway, there's been no single source of truth. So both NFT creators and collectors suffer. We believe there's a better way. OpenRarity provides a verifiable, consistent, and mathematically grounded approach to rarity calculations with open source code and everything. At last, somebody's come along and saved the environment. So let's have a look at the different types of platforms and how they operate. So we need to look at the trait distributions. That's the input data. So once the whole collection has been minted, say there's 10,000 or 9,000, or in the Bella Hadid model, 3-dimensional avatars based on her body, there's 11,111. So let's have a look at the Bored Ape Yacht Club trait distributions. So this is the background. Remember, there's like grey, yellow, light yellow, and so forth. So there's 1, 2, 3, 4, 5, 6, 7, 8 possible backgrounds. And look, they're more or less uniform distributed. So the color of the background doesn't add anything to the rarity. This is the earring. Most of them, like 70%, have no earring, but just a few of them, like 10, have a cross earring, okay? And there are other distributions. For example, the mouse, there's some really, really rare mouths as well. And the black suit is the rarest clothes. Blue beanie eyes are relatively rare. And some of these mouths are, have very, very low frequency. The unknown pizza mouse, for example, possibly the rarest attribute over all the different traits. But it's actually a bit more special to have one of the rare earrings than it is, sorry, to have one of the rare mouths than it is one of the rare earrings. And I'll talk about that in a minute when I talk about the trait normalization. So all of these are links to different platforms. For example, Nansen, I mentioned before. So you can have a look at all their literature, how rare is rare, how they measure rarity, and this sort of thing. And I've summarized all these 20 different websites. And Nansen used something called the arithmetic mean. In other words, they look at the rarity probability. For example, they take this probability, this is the frequency of grey backgrounds, say 0.15, and then if it's got a silver stud, add this, and then add this, and add over 1, 2, 3, 4, 5, 6, 7 different traits, at least for Bored Ape. Some collections have 20 different traits. And anyway, they just average the arithmetic average of those frequencies. And that sounds, even though Nansen's a great site, does sound a bit odd, adding probabilities. I mean, okay, if you want the probability of A or B or C, and A, B, and C are all mutually exclusive, then you might add them. But in fact, well, it's explained in more detail in the paper. This is exactly what cannot happen in these collections. You want the probability of A, grey background, and B, cross earring, and C, pizza mouth, etc., etc. So for that, as long as they're independent, you would multiply, you'd take the geometric, these are means, okay? Because you can have an arithmetic mean, which, you know, is divided by the number of traits rather than just adding them up, which is what you do in probabilistic term. But when you scale something, it's not going to change the ranking of everything, because everything's scaled by the same amount. And the final ranking from 1 to 10,000 won't be changed by dividing by 7 to take the arithmetic average. Or indeed, if you multiply them, which sounds a lot more correct, certainly in the case of Bored Ape, where the traits are independent, if you take the power 1/7 or the 7th root of that product to actually get the geometric mean, you'll still end up with the same ranking from 1 to 10,000. And then there's the harmonic mean. I'm going to define these in more detail. These are what we call the Pythagorean means, okay? And then there's the minimum, which is the rarity traits, when it's called rarest trait, or I can't remember what they call it. The language in terms of, you know, what is a trait, what is an attribute, what is a score, what is a rank, it's all over the place. So it's a bit like when I first went into crypto. You know, understanding terminology was really an issue. But you know, we've moved a long way in the last few years in standardizing terminologies. It's not perfect, but it's a lot better. So these some of them I had to back out because there's no documentation, but I just, well, Casey, my co-author, compared their rankings for lots of collections with one of our bits of code. For example, the harmonic one matched the how rare is one that we didn't have any documentation for. So the star means that, for example, for the Rarity Tools, we just matched, sort of reverse engineered. And some of them are unknown. It's not possible to, we could reverse engineer them, but we still couldn't identify any methodology. Now, the OpenRarity one that's coming along to save the day uses a surprisal ranking algorithm based on the information content. And there's, the only documentation is this equation here. So this is based on the Shannon entropy, like the sum minus log 2 of the attribute frequencies. They call them probability of trait I. Okay, so I would be 1 to 7, and then you'd put in the probability of having the background, and then for I equals 2, the probability of, well, the frequency in of the earring. So, but if you add up the logs, it's basically the same as multiplying the probabilities, as long as what you're doing, this rarity thing, is invariant under taking logs. And in much the same way as, if you divide by 7, it's not going to change that final ranking. The log is a monotonic transformation. So, it doesn't matter whether it's monotonic, increasing or decreasing, which, because some of them are decreasing. In fact, this is a decrease, it's minus log. So they change the ranking around so that the one with the highest score is the rarest. There's so many bits of string and elastoplast. And here's another one. This is the NFT Go Rarity model. That's the one that raised quite a lot of money for this. And they're using something called Jacquard distance. So it's not based on entropy. It's not based on some statistics, apparently. It's based on, one of these hundreds of different distance metrics like L2 norms or Hamard distances for binary strings, or this is the Jacquard distance, which is very similar to the Hamard distance, actually. So these are different methods, maybe, but then, hang on, wait a minute, what did I put here? OpenRarity is geometric. Well, I've given you a heuristic proof of that. NFT Go is just the same as the arithmetic, the same as the Nansen one. And how on earth they've managed to put so many resources behind this one and this one without doing a few basic bit of basic maths, it's astonishing. So, yeah, this is where quants need to be. The grass is very, very green here. So how are these PFP collections generated? So the generator starts off with setting a very large number of the tokens, and each token is a certificate of ownership of an avatar. And these avatars, I haven't had a chance to show you the videos of the Bored Ape metaverses, but they're three-dimensional avatars now in Bored Ape Yacht Clubs and other Yuga Labs metaverses. So you set the traits, for example, background, gender, hair, eyes, and clothes. Maybe there's 5 traits. And then each trait has a certain number of attributes. For example, you could have 10 possible backgrounds, 3 possible genders, 4 hair attributes. You could also have none, like no hair. 5 attributes and 8 clothes attributes, for example. And no 2 avatars will have the same set of attributes. Every avatar is unique. So that means in this case, we could actually generate 10 times 3 times 4 times 5 times 8, so that's 4,800 different avatars without having a repeat of any of the set of attributes. But in the Bored Ape Yacht Club, we could generate 1.3 million unique avatars, but actually only 10,000 were generated. In fact, there's a nice little bit of machine learning code you can find quite easily to generate a fake Bored Ape, one that looks exactly like other Bored Apes, but isn't actually in the collection. Again, for lack of time, and there's so many things to talk about here, I won't go into that right now. So at last, a little bit of maths. So let's call the traits x1 to xn. For example, n is 7 in Bored Ape and 10 in CryptoPunks. The ID of the token, which we can call AK, for k equals 1 to 10,000, is identified with this unique mapping of traits to the attributes X, I, J. So, for example, if trait 1 has 7 attributes, so CETA 1 will be 7, then the attributes would be x11, x12, x13, x14, up to x17. Maybe those are backgrounds. And a unique token might have a grey background. So that means that X1, say it's token number 5. So X15 would be equal to X13. Okay, but there are lots of other tokens with grey backgrounds. We want to find the number of other tokens that all have grey backgrounds. So this is the cardinality of that set, which we can also capture using the indicator function. So, for example, if 200 tokens have grey backgrounds, then, and background is trait 1 and J, so M1, 2, did I say for grey, or 1, 3? That's going to be 200. That's the number of avatars that have that particular attribute. It's the count. We could also model frequencies, and that's what most of the other websites that deal with ranking do. But on the one that I showed you, OutRank, we prefer to deal with counts. It's equivalent in the end, just a little bit less messy. Because each token has exactly one of each attribute, you could also say, you know, because the probability is the count divided by the number of attributes. So you've got, sorry, M is the, M is the number of avatars. So M is 10,000. So the probability, if there's 200 over 10,000, M is 10,000. And the sum of all the attribute frequencies is 1, otherwise it wouldn't be a distribution. So I showed you the background attribute frequency distribution, and the sum of the heights is 1. Or if we do it in terms of counts, the sum of the totals is 10,000. And so there is actually not a bijection, but an injection from the avatar to these counts, because although this is unique, this is bijective, there could be another avatar that actually has 200 here and whatever, 500 here. It doesn't have the same attributes, but this is not a bijective map. So attribute mapping is unique, but the attribute count need not be. And this is just putting it in the language of frequencies. And then now let's introduce the fundamental concept of a weighted power mean. So you've got any non-zero real number, P, and this is the power we're going to use here. And we don't want it to be 0 because otherwise we'd have infinity here. And A is any set of positive real numbers, and these are the weights, also positive. So these could be the counts, and these could be all equal to 1 if we like, if we have equal weights. They don't have to add up to 1. And so this is the definition of weighted power mean. You can find it on Wikipedia if you like. And particular values of P give us the different types of power means. And we also need some special cases for the limits because, for example, when P is 0, this you can calculate a limit, and this gives us the weighted geometric mean of the A's here. This is a weighted geometric mean. This is the weighted minimum when P goes to minus infinity. This is the weighted maximum. And the other two special values of P are +1 and -1. +1 corresponds to the arithmetic mean, and -1 corresponds to the harmonic mean. And if you can add equal weights, that's the normal arithmetic mean, or you can have unequal weights, and that's the weighted arith mean or the weighted harmonic mean. And then when it comes to trait normalization in this framework, that's where the weights come in. Because if there are a lot of attributes of a particular, like the mouth has lots and lots of different attributes. So that pizza mouth is very rare. You want to increase, if you set the A's to be equal to the attribute counts, you will increase the weight on those that have many attributes so that they're more important after the trait normalization. So with the Pythagorean means, the generalized means, the special cases, here we've got the ordinary minimum, the harmonic, the geometric, and the arithmetic means. I've phrased these in terms of probabilities because that's what those 20 existing ranking sites do. And I call them the rarity measure on the minimum, the harmonic, the geometric, and arithmetic. These have a well-known ordering. So if you take the same set of probabilities, the minimum, the smallest of all those probabilities or frequencies, will always be less than the harmonic, which will be less than the geometric, and the largest will be the arithmetic. So in order to compare these different measures, and one site might use a harmonic and another site use an arithmetic on a similar scale, I propose that we always, and some sites already do this conversion, but not all, and then they call score something else. So this is my definition of a rarity score. And that is the measure is mapped to the domain 0, 1. So that, and use just in a simple way as usual, taking off the minimum and dividing by the original support. And so every rarity score can be comparable across different methods. You can compare the harmonic with the arithmetic. And then you can also convert this measure into a rank, which is a number between 1 and m, where 1 is the most rare and rank m is the least rare. And if you want, you can go first to the score and then to the rank. It doesn't make any difference. Ranking the scores or ranking the original measures, you'll get the same ranks for all the tokens because this is just a simple linear transformation, which isn't going to change the ordering here. Now this Pythagorean mean ordering that I mentioned before, where the minimum for any particular avatar, it's according to the min, it would be less than the harmonic, would be less than the geometric and so forth. But once you convert it into scores, that ordering is lost, or indeed to ranks. And in fact, the correlation between two scores derived from different metrics can actually be very low. It depends on the collection and it depends on the metrics. It tends to be a higher correlation between the close ones, like the correlation between the scores, the geometric scores and the arithmetic scores will be higher than the correlation between the min scores and the arithmetic scores, because these are closer. And we can also look at score distributions. So these are derived from harmonic in blue, geometric in green, and arithmetic in red. So these are the relative frequency plots of the scores themselves that have support 0, 1, as I said before. And you can see that, for example, in Bored Ape Yacht Club, according to harmonic, quite a lot are going to have a low rarity score. So they'll be clustered around that ranking 1. They're still ranked 1, but you'd get to rank 8,000 by here, you know. Whereas if you use arithmetic, you'd need to have a score of 0.8, and that would be the rank of 8,000. And this is also bimodal here. Geometric looks sort of log normally, but it doesn't here. Here you've got a bit of bimodal there. And it's the arithmetic here. You do get a sort of shift in the mode from here to here to here. And from here, you can't really tell about the Doodles collection. But there is a shift in the mode, if there is a mode, Anyway, they're all very, very different. And when we're dealing with hundreds of collections, it's difficult to know how to summarize this information. This just shows you the actual, the rank correlations, Spearman's row, Kendall's tau. This one is always less than the Spearman's row, or the Pearson's correlation, the actual scores rather than the ranks correlations. But you can see, look, this is like really small for doodles. This just tells us what we already saw at the beginning, that the ranks you get are completely different depending on the metric applied. And then we can look at the effects of trait normalization and plot their distributions probably here. I think I already showed you some on the NFT site that I've built up with OutRank. So we can look at the effect of trait normalization on different sorts of collections here, where you switch it on and off. And these are the score distributions, just as I showed you before. And then the comparison, for example, the geometric, what's the effect of trait normalization? Doesn't often change a lot, but in some collections it does. I'll get back to that later on the talk, the next bit of that website. So it's very simple, and this is proved in the paper, it doesn't take very long, that the rarity scores are invariant or they're reversed under increasing or decreasing linear transformations of the raw rarity metric. So that means that it doesn't matter whether we use counts or frequencies. That's a very simple transformation. We're either going to take a p to the power or not, or we're going to divide by p, divide by n. Or none of these things are going to change the scores. As long as it's a linear transformation, so dividing by n is fine, or doing the score thing itself. But for the actual ranks, they are even more invariant, but under strict monotonic transformations. Rarity scores aren't, but ranks are invariant under whether they're monotonic increasing or decreasing. But these monotonic transformations do change the rarity score. They make the distribution more leptokurtic when you've got a convex strict monotonic transformation. Again, all these results are in the paper. These results allow us now to have a look at this OpenRarity calculation here, which this is the only documentation they have other than a video about Shannon Entropy, and to classify it as a geometric mean. The Jacquard distance is a little bit more difficult. This is the, that's what I showed you before. This is the documentation, which took me a while to disentangle, but with a bit of a touch it and see checking, I realized that I'd got the right, in our methodology. So using these bijective maps that I mentioned before for two different tokens, the Jacquard similarity is the proportion of attributes in common. So you can express it like this. And then the Jacquard distance is 1 minus the Jacquard similarity. And you can already see that this is like an arithmetic mean. Well, not quite, because we're adding up to n rather than across m. But the trouble is that NFT Go divide, that they take the arithmetic average of a token's Jacquard distances from all the other tokens. Now, I can see why they do that, because there's no reason why in a Jacquard distance you would use any other operator than addition. There's really no basis in using multiplication or division. So yeah, why not take the arithmetic average? Only the problem is that now with this arithmetic average, we can then in 3 lines show that by reversing the order of summation, that the Jacquard distance is 1 minus the arithmetic mean. So both these two, maybe the reason ultimate guide for Jacquard distance and the OpenRarity didn't see that they were just doing the same thing was that they did have decreasing transformations of the geometric mean and the arithmetic mean. But then they obviously reversed the scores because the touch it and see method shows that that's how they do the ranking, with the high scores than the low scores. So finally, let me look at a few collection characteristics. This is trait independence, which it's easy enough to see that when the traits are independent, then multiplying their trait frequencies is statistically correct. So this is Bored Apes, and I mean, there's a bit of small sample, even though it's 10,000 in the collection, for these contingency tables that underpin background clothes, for example, this is a chi-squared test, so there's a whole contingency table behind there, might have some sparse elements. So there is a bit of measurement bias. That's why we look at the Kramer's V here, which is pretty indicative. There's no test here. These are tests. This is the under here. This is the critical value of the relevant chi-squared for that contingency table. And this is the value we get. Bold show a exceedance, but not particularly large. So I would say that the collection was designed with independent traits. And then these barcodes, I was trying to find a way, because we've got hundreds of these collections, how to summarize the characteristics of the. So one of the things that I designed, something called the barcode, is the maximum trait frequency minus the minimum trait frequency, because you know that ranking of the Pythagorean means, when you've got the minimum, then you've got the harmonic, geometric, arithmetic max. Well, the bigger the difference between the max and the min, the more scope there is for different results to come from the arithmetic and the harmonic, for example. So if you've got just very low lines here, then some of the collections have everything more or less lying along this 45-degree line. This is the rank according to arithmetic and the rank according to harmonic. And because the harmonic has a very bimodal distribution for Bored Ape Yacht Club, also for doodles, we find these clusters where, and they are very different because this is quite high, and so is this, where you see all these tokens, and you know, we want to be able to just plug in the token ID and just go bing, and it shines up here or here or here or here. And so when, you know, you've got something that's really, really common according to harmonic, but, you know, in the lower quartile, one of the rarest according to arithmetic, then you know that you should be putting your token on arithmetic ranking sites, because they're going to make it more rare, and therefore you could get a higher price. And the opposite is the case if you've got something down here with arithmetic, say, is really, really common, but harmonic says, hey, this is one of the most rare we've seen. And there's lots of tokens like that in all the collections. And yeah, anyway, I won't go on too much about these QR codes because I'm sure I've spoken for long enough already. So here's the main results. Rarity ranks are invariant under strict monotonic transformations, which means that all the rarity metrics in the public domain are equivalent to one of 4 different methods. And when it comes to rarity scores, they are invariant to linear transformations, or they would be reversed if it's a decreasing one. The geometric mean count or frequency doesn't matter, or any strictly monotonic transformation like the OpenRarity is a statistically correct rarity metric to use, but only if all the traits are independent. And most of them that we've looked at do not have independent traits, doodles and CryptoPunks, particularly doodles. There's a lot of dependence between the attributes that are chosen there. So that means that most of the rarity metrics in the public domain are not statistically correct, and we need an entirely different approach to measure rarity accurately. So just to say, if you want to take a, put your camera up there or just click this, you can go to get more details from OutRank. So I'll stop sharing my screen and back to you, Alexander. Assuming you're there.
Most of the costs in this.
That was fantastic, Professor. Thank you so much.
Shall I just stop the recording now?
Right now on the final
Yeah, yeah.
details,
That was wonderful.
we'll just framework it for you. We'll include, everything, and then if you need to make any